Okay, let's get started. Linked list algorithms, let's do this. 54 slides, ooh baby. So last time we talked about what a linked list is. Now let's do some stuff with that. So we just left it at mostly the structure. We did toString, which was an algorithm, but now we want to add quite a few more algorithms to that. We want to talk about how to work with these linked lists. We know the structure is each node is an object that knows the value at that point of the list and a reference to the next node. And then we link these nodes together through those references with the next reference to be able to link together a whole list and have our linked list. And it bounces all over memory by following references to be able to get to where we want to go on the list. So we know all that. Let's get into working with this and doing some more interesting things, because big deal we have a linked list, but we want to be able to ask that linked list questions about the data. Things like how many elements do you have? Size will be, I think, the first one that we'll do, aside from toString that we already did. Okay. Before we talk about that, we need to talk about generics. As promised, I foreshadowed this a little bit, but let's do it right now. So we saw this code last time. We created our linked list, but it was a linked list of ints. It was linked list node int, which, cool. If you want to store ints, fine. But what if I want to store literally anything else? What if I want to store doubles or strings or ratings, which is going to be our use case for the homework? We want a linked list of ratings, eventually a linked list of songs and a linked list of ratables. We want different things. Actually, with ratables, I think we go to array list at that point. But we don't want to just store ints. What we want is to be able to take in a generic type just like array list does. Array list says, I don't care what type I store. Just let me know. Give me a heads up of what type you're going to store in this data structure, and then we'll do that. So if I do array list of integer, I'm going to get an array list that can store integers. If I do array list of strings, I have an array list that can store strings, etc. This is how we use array lists whenever we've used those. We want the same thing with our linked list. We want our linked list to be able to take this type parameter, which is what I'm going to call it, and work in a more generic way, which is the way Java calls it, what Java calls it. And this is how we'll do that. These are Java generics. In most languages, they're called type parameters, so I like to still just call them type parameters. That's the more broad term for this concept. But in Java, in the world of Java, if you see the word generics, they mean type parameters, and they mean this concept. So Java generics, we're going to specify a type variable, which can be any type at runtime. When we create a linked list node, we're just like array list, we're going to specify what type we want to store in this thing by specifying what the type of T in this example is going to be. So let's break this down and look at the different parts of this syntax. First, when we define the class, we're going to say that this class is going to take a type parameter by using these angle brackets and specify a type parameter list. So this is just like a parameter list that we have in parentheses. Well, I shouldn't say just like, but it's a parameter list like the parameter list we have in parentheses. And it can be multiple names, and each name is going to be the name of a type that can be any type in Java, asterisk, except primitives. It can't be primitives. And I say a parameter list, even though we're only going to have one for our example here, but for say, a hash map that has a parameter list that takes two different types. So they'll have, if you look at the hash map class, they'll have a type parameter list in angle brackets with two values, capital K, comma, capital V, is going to be what they call their type parameters. When we name these types, I chose T here. That is a variable name. It's a variable name, and that variable stores a type. And I chose T just because that's what I chose. Or maybe that's what Paul chose. Maybe he wrote this code. I don't remember. But T for type. is what we're using here. The name here isn't super important. It can be anything. There's nothing special about capital T. That's just the name that we chose, just like choosing the name for any variable. Except naming conventions, we typically stick with one singular capital letter when we're specifying type parameters. I don't know exactly why, but that stuck throughout industry. So if you see a variable name that's just one single capital letter, you better be thinking, hey, this is going to be a type variable. This is a type parameter in this case. So capital T, if we'll use capital A sometimes. I think an example later in the semester, we use capital A. Array list, I forget what it was when we had the code up, but either A or V, I forget what it was, something. But whatever letter is chosen doesn't matter so much. It's a variable name. It should make sense, like K and V for key and value in HashMap, makes sense. But this is a variable name, and then whenever we want to specify that type, the type that's stored in this variable, we're going to use that capital T. That's effectively a placeholder for a type that we don't know about yet. When we're writing the linked list node code, we don't know what type we're going to get. We can have multiple linked list node objects out there with different values for their type parameter. If somebody creates a linked list of integers and a linked list of strings and a linked list of doubles and a linked list of songs, we don't know what those are going to be. It could be types that don't even exist when we write this code, but will exist later in the future. Somebody will write it. We want our code, our data structure, to be able to take any type ever. So what they'll do is specify what the type is through the type parameter, and then all of these T's throughout the code will effectively be replaced by that type. So we use T as a placeholder wherever we use the generic type. And we use it just like any other type. We have an instance variable of type T. We have a parameter of type T. And we can even have other type parameters of type T, or type arguments in this case. We're on the other side of things. A linked list node of T. So a linked list node of T should have a reference to another linked list node of T. And by doing this, we're restricting a linked list to be all of one type. I can't have a linked list node of string, storing a value of a string, referring to a linked list node of double that stores a value of a double. We don't want to mix our types like that in Java. We could, if we rewrite this class, we certainly could do that if that's the kind of linked list that we wanted. But those linked lists are hard to work with in a strongly typed language if we're mixing types. So we're going to have next be another linked list node of T. And then when I actually create a linked list node object or variable in this for this highlighted box, again, over on this side, it's implicit that this is of integer. So you can think of integer being right here. And in fact, you can type integer if you pull up this code and type integer right there where my cursor is. The code's still going to function 100% the same, except IntelliJ will say, you don't have to type that there. It'll gray it out and say, why'd you even bother? I already know that it's integer because you told me it's integer right here. One of the few cases where Java will let us shortcut things a little bit. So we're specifying the type parameter. We're saying T, every place where there's a T in this class, for this specific object of that type, T is going to be integer. It's not actually replaced. I see this every semester. I don't know how to word this in a way to prevent this. I think it's just part of learning how these work. But it doesn't actually replace the type parameter. So do not go to your linked list node class when I say I need a linked list node, linked list of ratings in homework 3. Give me a linked list of ratings. Do not go to the linked list node code and change T to rating. That's not going to have any effect because T is a variable name. You're just changing that variable name to rating, which doesn't change any of the functionality of this code whatsoever. It doesn't change it at all. When you want a linked list node of ratings, you'll say linked list node of rating when you create the variable that's going to store a reference to that linked list. So in your song class, not to give too much away, but in your song class, your instance variable would be of type linked list node of rating, and then effectively, not literally, but effectively for that specific linked list, T will be replaced with rating. You do not actually change that in the code, though. because I want a linked list node of integer. I want later on a linked list node of string. This code does not change. The code in the linked list node class, it's a little muddied because my main method is in the same class. But this code for the linked list node class in data structures linked list node, that class, ratings.datastructure.linked list node, that class, you don't have to change that code at all. That stays with T's everywhere in that code. But when you create a linked list node, specify what type you want, and I can have one linked list node of string and one linked list node of integer, one linked list node of ratings, and I'm reusing the same exact code for each of those linked lists. That's type parameters, or as Java calls them, generic types. Any questions on generics? I don't know what else to say about these. It's mostly new syntax. It is a new concept, but if that's not making sense, I want your questions. I think it should mostly make sense. Just because we've been using these with array lists and hash maps all along, you're just seeing the other side of it now, of how do we write a class that takes type parameters. I don't think it's too much of a leap, but if it is, maybe it is confusing, maybe it isn't. If it is, ask me. Ask me questions. I'm here for your questions. If I wasn't here for your questions, I could just point you to the video from last semester when I said the same exact stuff. Muhammad Ali, that's a good name. All right. Well, I'll watch chat, see if there is a question coming in, but I'll get there. Well, let's introduce what we're going to do next, because that's all I have to say about type parameters. That's it. That's what they are. And we're not going to go deeper into that. If we do use something else with type parameters, I'll bring them up again and talk about the new stuff. For example, you can have methods that take additional type parameters instead of a class that takes a type parameter. You can take, I mentioned multiple type parameters, but we can also have a type parameter in a method that's different than the type parameter of the class. We can mix these. We can do all kinds of weird stuff. But this is all we'll need for the class. Will our code still compile if two nodes are made of different data types? Yes. Yes, yes. Oh, no, in the same list, do you mean? If you have two different lists of different types, that's fine. Like you can create an array list of integer and on the next line an array list of double, that's perfectly fine. If you mean in the same linked list, no, it won't. If you try to set next to, we just introduced the getters and setters on the slide. So let's add some getters and setters. They're introduced now. We're going to use our type parameters here too. If you create a linked list node of integer through the constructor and then try to call set next on a linked list node of string, that's not going to compile. Because for that linked list, let me go back to the other example. For this linked list right here, I'm creating a linked list of string. That means everywhere in the code, T is replaced by, T is replaced by string, right? So if I say this is a linked list node of strings, then this is string val linked list node of string. So in the constructor, if I put an int right here, for example, then int is not going to match string, so I'm going to get a type error right away, right there. And if I try to add a node, more directly to your question, if I try to add a node using set next to a linked list node of integer, then for that specific object, that T in set node or set next, that T is going to be integer. So if I give it a linked list node of string, again, I'm going to get a type mismatch because the type parameters aren't the same there. But if I want to create a brand new linked list node through the constructor, and I say, give me a linked list node of strings, and I give it a string, and I give it either null or another linked list node of strings, then that's going to be fine. So across different linked lists, the types have to, or across different linked lists, the types can be different, but within the same list, they all have to be consistent, the way we have the code written here. Because it's always T, if T is one type, then set next always takes that type, next always takes that type, the value always takes that type. It's always that type throughout the entire object. What's the point of using type parameters when you end up stating the desired variable type when creating a new linked list? It's that we can have multiple linked lists with different types. So I write the code one time, and that linked list code works for every single type ever. For example, when the Java developers wrote the ArrayList class, they didn't know we were going to create a song class. They didn't know we were going to do that. They didn't know we were going to create a ratings class. I should use ratings because that's the first linked list we're going to create is of ratings. They didn't know we were going to create the ratings class. But their code still works with that type. If we say new array list of rating, that still works because they use type parameters. So it makes our code much more flexible, and especially in our data structures, we want type parameters in our data structures because it lets our data structure store any type. It removes our data structure implementation from what we're going to store in that data structure. We say, this is how we store things in our data structure code, and then whenever somebody actually wants to store stuff, they say, okay, I'm going to store ratings in that thing. And we say, okay, my type parameter is rating for this instance of this data structure. So flexibility is the big thing. Otherwise, we have to do what we did on Monday and say, writing our linked list code, we have to say, what type is this going to store? I chose int for that example just because we didn't want to talk about type parameters when introducing linked lists. I said, well, we're only going to store ints. I can't reuse that code and store a linked list of strings. But with a type parameter, I don't care what the type is. Something that doesn't even exist yet, fine. Our linked list code now works for that type that doesn't even exist yet. Yeah. Type parameters cannot be primitives, is the reason, yeah. And I kind of wish they could be just because I would never use the class types for the primitives ever. And then I would never have confusion about that. Because the average method, I think, is the first time it comes up. People want the average method to return a capital D double. That will 100% of the time create an error in Autolab. And I've said, never use the class types unless you have to. And enough people don't heed that warning. I feel like I spend too much time talking about that during that lecture, too, but I still see it a lot in office hours. I have notes in the auto lab, too, but anyway, this is the only time that I'll ever use the class types for the primitives is for type parameters, and it's because you can't use primitives. It has to be. Yep. Yes. So if you want a method, and this isn't something we'll require, I think I have one example in this semester, but I don't think I ever asked it on the homework. You would put a type parameter on the method itself. So you're saying this type parameter isn't here, and you want to write a method that takes a linked list of node of t. You would put the type parameter right here, using the same syntax. And then it'll work fine. Okay, so here's our getters and setters. When you're doing getters and setters, if there's something you don't want your users to change, just don't give them a setter. I don't want anybody to change the value of a linked list node. It's just, I don't know why. It's just not a use case. Actually, I know why. It's because we used to do this course in Scala, and Scala didn't let you do that, and I just kind of transferred that over. Because I never built any example where we want to change a value because of that. Anyway, but if you don't want them to change any value, just don't give them a setter. Easy day. We have a private variable, no setter. That means the value cannot change after you create a node. And let's build these methods. Now that we have our getters and setters, because we have private instance variables, if we don't have getters and setters, there's no point in having this data structure at all. So with the getters and setters, we can start writing more algorithms and doing more stuff with this linked list node. And we're going to build these 4 things. This is what we're going to do today. Size, just asking a linked list node, hey, how big is this list? Append, adding an element to the end of the list. On Monday's example, we effectively pre-pended. Whenever we added a new element, we added it to the front of the linked list, which is a lot easier than appending. With appending, we have to find the end of the linked list first and then append to the end of it. Pre-pending, you already have the front of the list. You create a new node and have it point to the old head of the list. Append, a little more work. Find, here's a value. I want to know the first instance of a node that contains this value and return a reference to that node. And min, the big one, hopefully we'll get to this. I'll try to go at a healthy pace so we can get to this. Min, give me the min value of this linked list. And this is the one that will most closely mirror what you're asked to do on task 4 of the homework for reasons that I'll get into when we get to that one. The first 3 are going to be structured just a little bit differently than what I expect on the homework. So, but it'll get the concepts out there. And of course, we're going to use recursion for all of them. So we'll get 3 good examples of recursion before we get to min. So let's get into it. So the size of a linked list, here's the algorithm. Make a linked list from 2 stack frames. Suppose we only call one method 2 times. I'm not positive what you mean from that. We can create a linked list with 1 stack frame, I guess. New linked list node, like just the constructor stack frame is all we need to create a linked list of size 1. But each time we add to the linked list, it's another constructor stack frame to be able to do that. I'm not quite positive what you're getting at, though. So I might have misinterpreted that. So size, we want to count the number of nodes visited. So we're going to use recursion here and count the number of nodes. So our first kind of meaningful, useful recursive method. So let's break down recursion a little bit more in this example. We have 2 basic steps to every single recursive method. One is our base case. This is a situation where we have a trivial input-output behavior. If I'm asking a linked list node for its size and its next is null, well, I got myself a linked list with size 1 and I'm just going to return 1. It's an easy thing to compute, no work to do. We're going to say if we're at the end of the list, this is a linked list of size 1. Easy day. Then the other side, if we're not in the base case, we hit the recursive step, which is where we're going to make a recursive call. We're not going to do much work here. We're only going to do a little bit of processing. We usually like to do as little processing as possible in our recursive step, and then make the recursive call to do the rest of the work. We're going to make a recursive call, assume that the recursive call does what it's supposed to do, and then we're going to do some extra calculation to get the overall answer, including this node. So for our case right here, we're going to ask the next node for its size. It's going to return how long, if it were the head of the linked list, how long would that list be? It's going to return some answer. So if this node knows that everything after it, there's this many elements after it, and it's going to account for itself, it can just add 1 to that and then return that value. Yes? Yes. In this case, that's a good question. When we get to min, we'll mix this up a little bit. But since size is a method of the linked list node class, we can't get into this method call if the node was null, because we wouldn't be able to call the method at all, because we wouldn't have an object to be able to call it on. So outside of this code, we would have to check if I have a variable that stores null, then the linked list size is 0. If it's not null, then ask it for its size. So this method will never return 0. We need some other way to represent that. You can add methods. You can always add methods to any of the classes. If you want to add to the linked list node class, you want to add new classes, new methods, you can add whatever you want to your homework code. Don't remove things is one caution. And the methods that you add, don't call them from your tests. That's a common thing that we miss. I try to put it in the homework docs all over the place and mention it in lecture. Anything that you create, don't access it from your tests, because what I do during grading is I take your ratings package and your tests package, and then I take your tests away, I put my tests in and run them to check it against your code. Then I put your tests in, not specifically in this order, but your tests and your ratings. I take your ratings away, put in my ratings package, and run your tests. So when I have my code and ratings in your tests package and run your tests, if you're calling methods that you created, those methods won't exist in my code, and I can't effectively grade your tests. So just don't call those things from your tests, or else you'll get errors in Autolab. That's my one big caution with that. But if you're writing extra classes, methods, packages, whatever, and you're using that code inside your ratings package to get stuff done, knock yourself out. Go for it. I actually love seeing that because you're creating software and being creative, designing architecture, things like that. It's really good practice. Same thing goes with your tests. If you want to create extra classes that contain helper methods in your tests package, that's fine too. Just make sure you're only calling them from your tests package, from other classes in your test package. Don't mix and match. Don't create things and then call them across ratings and tests. And that way we can, like if you're only testing methods that are defined in the homework doc, then your tests, we can communicate. I can write tests, you can write tests, and they're going to work. Your tests are going to work against my code. My tests are going to work against your code. But we have to stick to the homework doc whenever we're crossing from ratings to tests and vice versa. What's a helper method? It's a method that, what's my succinct definition? I'd say it's a method that's not part of your public API. So it's a method you write to make your code work, but not a method that anybody else is going to call. Only you are going to call it just to make your other functionality, your other methods work better. Okay, and for these, I'm going to do what I call abbreviated memory diagrams. I'm going to use these visuals, these diagrams, because if I go through memory diagrams in the tracing tool for each of these, I'll probably only get through one of them. But let's see how this size method works. So somebody calls this method. Somebody has access to the head of a linked list. In this case, that head has the value 4, and asks for its size. We're going to ask the head node for its size by calling this method, and it's going to check if next is null. That's going to be false, so it's going to go to its recursive step. It's going to say this.next.size, so it's going to go to the next node and ask it for its size. And that node also doesn't know the size. Neither of these have been able to do anything yet. All they're doing is making recursive calls. This node is going to make another recursive call and ask the next node in the list, hey, what's your size? And each node here, importantly, is going to think that it is the head of its list. So when I'm asking this node for its size, I do expect this to return 1 because it has no knowledge of this other node. This call to size, it would happen to be recursive here, but this call could have been made from anywhere else. It could have been made from the main method. That node has no knowledge of where this call came from. So from its perspective, it is the head of a linked list. So its size is actually 1. It's going to check null, or it's going to check its next. It is null. So it says, I'm a list of size 1, or I'm the end of a list, whatever. It doesn't know. But it's going to say, I'm a list of size 1. It's going to return 1. This node got its return value from its recursive call. It's going to add 1 to that to account for itself and return 2. And this node is going to get that return value of 2 from its recursive call, bump that up by 1, and give the answer to, since it did happen to be the head of the list, it'll give its answer to the original caller. So what we effectively have on screen when we have a linked list, we like to think of this as a linked list. It's a linked list containing the values 4, 3, 1. But to the code, what we actually have here are 4 different linked lists. We have the linked list of size 3, a linked list of size 2. Oh, I should circle the whole thing. A linked list of size 3, a linked list of size 2, which appropriately returned 2 for its size, a linked list of size 1, which appropriately returned 1 for its size, and a linked list of size 0. If we have just the value null, that's going to be a linked list of size 0. That's how we'll end up representing an empty linked list, is just null, not, and I see this every semester, it drives me nuts, because I don't know what else to say. I just repeated a bunch in lecture. But do not, to represent an empty linked list, do not say new linked list node of null null. That is not a linked list. That is an empty linked list. That is a linked list of size 1 that stores one value, and that value is null. Common misconception. I see where everyone's coming from when they do that. It's not the worst thing in the world. It's frustrating because it's one of them things I see all the time, and I don't know what else to say in lecture to get you to stop doing it. But just don't do it. Does Java? Yeah, we can. Java's array list does keep track of it. I think its linked list might as well keep track of how many elements are in it, so it's O of 1 instead of O of n. This is O of n. We're not worried about efficiency at this moment, though. We're worried about how to work with a linked list. But we would. Actually, we can't. No, it can't do that. We can't keep track of a counter. Because if we go like halfway through a linked list and remove a node by manipulating some references, how's the overall linked list know that change happened? We don't really have a good way of doing that without adding a lot of extra mechanisms to this thing. So we could, but it'd be pretty complex, as it turns out. Well, yeah, but it does. It sure does. Okay, so removing a node, they have to do some extra work to make sure the size is updated appropriately. Now I'm wondering how they do that. I'll look at some other time. All right, so let's append to the end of the list. Append, similar to prepend, we're adding an element, except we want to add it to the end of the list, not the beginning. So to do that, remember, when we have a reference to a linked list, we only have a reference to the head node, the first node of the linked list. So we have to do some work just to find the end of the list first and then append to it. And before this one gets pointed out in chat too, we could always store a reference to the last node as well. Make this O of 1. For sure, this one would be an easy one to do O of 1 with. On Friday's lecture, when we build a queue, we're actually going to do that. We're going to store a reference to the head and the tail or the end of the linked list. But we're not going to do that yet because we want some practice with recursion and stuff. So we're going to find the end of the linked list, and if we're at the end, then we append. So if next is null, we're at the end of the list, and we can set next to a new linked list node with the value we're inserting. Otherwise, we're going to punt down the road. We're going to tell the next node, hey, append this value. So we have this linked list. We want to add a value. We tell the head node, hey, append 1. That node says, sure. But my next isn't null, so I'm just going to tell the next node to do it. The next node gets this call, gets the recursive call, and says, well, my next is null, so I'm going to add this node. I'm going to create a new linked list node and set my next, which is currently null, to a reference to the new node that I'm creating with the new value that's added to the list. Creates that node, and this method does return void, so there's no feedback to the original caller that something was actually added. We have to have some faith in this method actually working, or ask the linked list for some information, maybe just its size, to check if the size increased by 1, if we want some feedback on whether this worked or not. Usually we just take it in faith that it worked. Okay, and find. So find, a little bit more work, and there's one key point that I want to make with this, is that our check for null is not the first thing that we do, and it must not be the first thing that we do. So what we'll do is check if the node we're looking at has the value that we're looking for. If it does, we're going to return a reference to the node. So we're not returning a Boolean here to say, yes, we found it, or no, we didn't find it. We're going to actually return a reference to the node, which in linked lists, the land of linked lists, is usually what we're after. Say we want to find a particular value and then insert another value right after that one. We want a reference to the node so we can have access to that particular location in the linked list. So we're going to return a reference to the node itself. So if we're calling this at a node whose value is equal to the value we're looking for, we're going to return a reference to that node by returning the keyword this, which stores exactly that, a reference to the node that called this method. How would you iterate through linked list values like you do to get its size? Me? If you're asking me, recursion. I'm not even going to talk about the loop way to do it. Most of y'all end up doing the loop way. I recommend not doing that, but I'm not going to cover it in lecture. But you can do it with a loop, if that's what you're asking. Use recursion, or else the tree's homework is going to be harder than it has to be, harder than it's supposed to be. So we're going to check if it's the value we're looking for, return a reference to that node. Then check if we're at the end of the list. So if we're at the end of the list, we have to make sure we check if that node has the value we're looking for first. And if it doesn't, and we're at the end of the list, then we can return whatever we're returning, in this case null, to indicate that we didn't find the value we're looking for. If you check for null first, you're going to check for null and say, okay, we're at the end of the list. But what you missed there is you never checked the last node in the linked list if that node contained the value you're looking for. And this is always something I see in office hours every semester, is writing a bug like that where you're never checking the last node, or sometimes never checking the head node. There's specific things in Autolab that are going to check for both of those. That if either one of those nodes has the value you're looking for our case of rating with the reviewer ID that you're removing, if either of those nodes has that, and you're not checking both of those and everything in between, then there's a bug in your code. Got to fix it. So if I swapped these two checks, I would have that bug. And if the value I'm looking for is at the last node of the linked list, I would never be checking it. It's a solid edge case, something we need to be testing for when the pertinent value is the last value in the linked list. Very important. Okay, so when we want to find a value, say I'm looking for 3, we ask the head of the linked list. It's the only reference we have. It's going to say, nope, I don't have 3. Let me ask the next node in the list. The next node says, I do have 3, yes. So I'm going to return a reference from this stack frame where this node is this. It's going to return this, so it returns a reference to itself, which is pretty tricky. It's pretty weird when you first see that. So it's going to return a reference to itself, and then we return that reference up the recursion, because each recursive call, we're just returning what the recursive call returned. Oh, side note, I did look up studied the tail recursion in Java. Like, even when we have, like, this is tail recursive, it's always tail recursive. That's fine. That's a fact. Like, it's just a tail recursive method. But Java doesn't care, as it turns out. Java doesn't do any compiler optimizations if you write a tail recursive method, which just really caught me off guard, because how could a modern language not? Like, why is Java not doing that? But I'm sure there's a really good answer for that. I kind of stopped digging deeper than that. But there is a good reason, and I lost interest after a while. Once they said you can't do it, whatever. So Java will not optimize tail recursive calls. All right, and if we ask for an element that's not here, I'm looking for 8. First node says, I don't have 8. Do you have 8? No, I don't have 8. Do you have 8? Well, no, importantly, the order here, no, I don't have 8, and I am the end of the list. So return, nope, 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 and we didn't get what we're looking for. Okay. Which brings us, we got through those quick enough. We got some time for this one. We got to talk about min. So min is a little bit trickier, and like I said, it mirrors what you're asked to do on the homework. If you haven't looked at it yet, first of all, why not? That's what we're talking about all this week is task 3, how to do task 3. So you should at least be familiar with what our end goal, where I'm trying to get you by the end of the week. And actually, I'm going to get you there by the end of today. We talk about stacks and queues on Friday, just kind of, I don't want to say bonus content, but it'll be interview only, I guess. It doesn't show up on the homework. Until task 8, you're supposed to use a queue, but not task 3. Anyway, if you haven't read it yet, it's the big one is, let me just start at the top. You're in the song class, you're going to add an instance variable that is a linked list of ratings, all the ratings that have been made for that song, then ways to add ratings to the linked lists and do the usual stuff. And the big one is removing a rating by a reviewer's ID. So it's a method that takes a reviewer, and then you have to go through the linked list and look for the first rating made by that reviewer if there's multiples. Find the first one, and then remove that node from the linked list. So we have to find rating by reviewer ID, and the equals method is not going to do that for us. So we cheated when we wrote the find method. When we just did the find method all of a few minutes ago, we cheated by using this equals method. This works, kind of, depending on the type, but the equals method has to be meaningful for this to make sense. In the ratings class, it's not going to be meaningful because there is none. You can write one, sure, but like we were saying before, when I take your tests and swap out your ratings package with mine, I'm not going to have one in my code, so you can't rely on that in testing. Actually, no, that's backwards, though, because you can rely on it for writing your remove reviewer by ID. So I guess if you did want to do this, that would work. And we can count on this existing, because the equals method exists in every single type in Java except primitives. But guess what? Type parameters can't be primitives. So when we have a type parameter, even though we don't know what t is, we can actually call the equals method on a value of type t, which is this dot value is type t. We can call the equals method because every single object in Java has an equals method. It also has a toString and a hash code, a couple other ones. Equals and toString are the ones that are most relevant to us, most immediately relevant. So we got away with this because it's one of the methods that every single object in Java has. But what happens when I want to write the min method? Min is going to need something like less than. I want to use the less than operator than that. You might want to use less than or equal. One of those two we're going to need some way of comparing two values for some specific order. And we don't have that. That's not equals, that's not toString, that's not hash code. It's less than. It's completely different. So we need a whole different approach, and we're going to do this more code than I expected on that click. But anyway, we're going to break this down. So I'm going to create a new class, this linked list of doubles, which is effectively a wrapper class. It has one instance variable, so we call that a wrapper class. It's just wrapping up this linked list of doubles, which I'm abbreviating LL node here just to save some space on the slide. But we have this linked list of doubles, and this is made to mirror the song class. The song class is going to have an instance variable that is a linked list node of ratings, and we have a linked list in a different class as an instance variable. The other three methods that we just saw and the toString that we saw on Monday, they were all written inside the linked list node class itself. And we heavily leveraged the fact that we had access to this, the keyword this, which was a reference to the node that we were currently considering for each of those algorithms. When we have this set up, which is going to mirror the song class, we don't have access to this, so we have to change the structure a little bit. We have to change our approach of how we do this min method. First of all, for at least the second time, never create a linked list node, an empty linked list node. Do not say new linked list node of null, null. That is not an empty linked list. An empty linked list is just straight up null. This is an empty linked list. We're initializing this to an empty linked list. And then when we want to add, I'm getting ahead of my slides here. We want to add to this linked list, the first thing we're going to do is check if it's null. If it's null, we're going to create a new linked list node to be the head of the linked list. If it's not null, then we know that numbers stores an object of type linked list node, and we can call the append method that we just wrote to append to that linked list. But we need to check for null, and we're going to have lots of null checks, and a lot of you will have null pointer exceptions as you're testing and submitting to Autolab. We need to check for null because null is being used to represent the end of a linked list. We're going to get nulls all over our code. And then min. We're going to have something to handle the special case of if the linked list is empty. These are always specified in the homework documents. What are you supposed to do when the thing's empty? I'm going to return -1, which doesn't make sense in this context, but I just needed something there, something that's going to be some value, some legal return value of type double. And then we want to start our recursion. This is the part we really got to talk about, because we were leveraging the fact that we had a reference to the node that we were currently visiting through the keyword this in our other algorithms, but that's not where you're going to have on your homework because we're not doing something that can work on generic types. We have to specifically call get reviewer ID from the rating objects. So we have a case where we want recursion to remember what node we're visiting and keep track of any information that we're working with as we're going through the recursion, as we're processing things. We want to do the min pattern that we saw in 115, but we have to move the information around a bit. So the problem is we need some recursion, but this takes no parameters. So whatever parameters we want on the recursive call, we're going to add a second method that we'll call a helper method that we'll call with some initial values to start the recursion. And then each step on the recursion node is going to be the node we're visiting, since we can't take advantage of the keyword this.